day everyone, today we will briefly present the results of our multi-sim laboratory experiments on series and parallel RC, RL, and RLC circuits, including the computations performed using Ohm's law and related circuit principles.
Now, we will walk through the RC circuit using the multi-sim simulator. The first thing we've done is we connected the AC source, the lamp, and the capacitor in series. And then after that, we insert the AC ammeter in series in 3 different places, by the source, by the resistor, and by the capacitor. We run the simulation for each placement to confirm the currents. And lastly, we connect the AC multimeter in parallel, the source, the resistor, and the capacitor. We run the simulation for each connection to record the voltages.
The computed values, we use the given specifications for the lamp, capacitor, and voltage source as a basis for all calculations. For table 1, we first determined the resistance of the lamp using the provided voltage and power rating. We then calculated the capacitive reactance based on the operating frequencies and capacitance value. Using these values, we obtained the total impedance of the circuit, which allows us to compute the total current. From this current, we determined the voltage drops across each component. The voltage drop across the resistor was found to be 148.2967 volts, while the voltage drop across the capacitor was 162.5503 volts. For table 2, we use the same total current obtained in table 1. Since the circuit is in series, the same current flows through both resistor and capacitor. Therefore, the current in both components remain constant at 0.3064 amperes.
In RL setup and multisim, we connected the AC source, the lamp, and the 1.389H inductor in series. We use an ammeter to measure current. We place it in series with the source, then with the lamp, and then with the inductor. In voltage, we use a multimeter set to AC voltage. We place it across the source, across the lamp, and across the inductor. After running the simulation each time, we recorded the current and voltage readings.
Now, I'll explain how we computed both the current and the voltages in our RL series circuit. First, we determined the resistance of the lamp using its rating R is equals to 220 squared over 100 is equals to 484 ohms. Then we computed the inductive reactance using XL is equals to 2 pi FL equals 524 ohms. With R and XL, we found the total impedance equivalent to 692 ohms. Using Ohm's law, I is equals to 220 over 692. We obtained a theoretical current of 0.3085 amperes, which we use in table 4. Next, we computed the voltages across each component. VR is equals to 149.3281 volts, VL is equals to IXL 161.558 per volts, and the total voltage is obtained using phasor addition. VT is equals to square root of VR squared plus VL squared is equivalent to 220 volts.
The RLC circuit is powered by an AC source with the lamp acting as the resistor, an inductor, and the capacitor. An ammeter is used to measure all the currents. It is put before the lamp to measure the total current. After the lamp for I1, before the inductor for I2, and between the inductor and capacitor for I3. These measurements confirm that the same current flows through all the series components. The voltage across all the series components are also obtained to analyze the behavior in the RLC circuit, as shown in the figures 8A to 8B.
For the RLC circuit, it has the different equation for the impedance, which is Z is equals to R minus JXC plus JXL. That gives us 484 minus J 530.5165 plus J 956.5019. For total current, we have the formula total current is equals to total voltage divided by the impedance. With correct procedure and solution, we have the total current of 0.341 ampere. Since it is a series circuit, the current for each component is also 0.341 ampere. For our voltage, using Ohm's law, we have the formula voltage is equals resistance times total current. Using this formula, our VR is 165.044 voltage, our VC is 180.9061 voltage, and our VL is 326.1671 voltage.
After that, we will use the percent error formula, which is percent error equals to measured value minus actual value over actual value times 100%. As you can see, there's a small difference between circuits and all of the circuits are not above 2%.
Thanks for watching. I hope this presentation helped you understand the basics of RC, RL, and RLC circuits and why they're important in electronics. Thank you and have a great day ahead.